thanks a lot for the introduction, which is not recorded. And thanks to the organizers for the invitation to give this series of 2 talks. So I guess before starting, I should apologize to some or many people in the audience who have heard me talk about at least part of what I will cover, and definitely most of what we'll cover today at various occasions already. But, well, that's how it is, I guess. And the aim of my course is to talk a little bit about local analytic aspects of kind of, say, emerging categorical p-adic Langlands correspondence. Right, and to give you an idea what I want to cover in this course, let me start with an overview. So let's start with G over QP, a reductive group. Like this overview will, of course, be very general and very imprecise. And I hope to be more precise a bit later. And then a locally analytic categorical p-adic Langlands correspondence aims for okay. Let me just write a fully faithful embedding of 2 categories. And I will say a bit about these categories in a second. Okay, so you have 2 categories. One is of representation theoretic nature, so that this is a derived category of, well, I guess I'll just write it in a term so that it makes sense, of solid, locally analytic representations of G of QP on QP vector spaces, well, on solid QP vector spaces, okay, which is kind of a derived version of a, well, more classical category of p-adic representations of these p-adic Lie groups that had been studied by Schneider and Teitelbaum, and that would put in kind of a solid context in the derived world by work of Rodriguez Camargo and Rodriguez Jacinto. And on the other hand, these are, well, the derived category of coherent sheaves, as I guess should be more or less obvious from the notation. And this space that I write here is, let me put it into quotation marks, p-adic, locally analytic variant of the stack of L parameters. Okay, so that's maybe the very rough idea or picture. And so even before saying anything about what these objects are, there is a word of caution due, that the rough formulation above ignores many features and difficulties. Many features or difficulties. So, for example, which is kind of an obvious thing, that I put a finiteness condition on the target, but I didn't put anything on the source. But in some sense, I don't want to talk about what kind of finiteness condition that should be. So, but I want to caution you that that you need to talk about something, need to add a finiteness condition on the right-hand side. And then there were on the left-hand side, thanks. And it's maybe at least a priori also not clear whether the finiteness conditions I put on the right-hand side is a correct one. And then there are things which have to do with whether fully faithfulness is really kind of true or can be true. Well, if these stacks are the one that I will introduce in a minute, and so on. So they were kind of, you should be careful with this kind of a formulation, but that's the rough aim. That's what you're aiming for. And my aim for today is I mainly want to work on the right-hand side. So introduce this kind of object that I just roughly called the p-adic variant of a stack of L parameters. And discuss additional structures for sheaves thereon. So I just want to understand a little bit what can be said about the right-hand side, basically. And we maybe also, but I guess we won't completely finish this today, describe what the desired functor should do on some interesting representations that you might have at your disposal on the left-hand side. So it should do on some interesting some explicit interesting examples. Okay, even though I guess I won't completely finish this today. And the aim for tomorrow then would be as to explain a relation which had been my kind of motivation to consider these things and objects in the first place, explain the relation to p-adic automorphic forms. And maybe to kind of families of overconvergent p-adic automorphic forms, so what's usually called eigenvarieties. Even though I do not want to promise you that I will define you what an eigenvariety is in case you don't already know this, but that's kind of in the background, and that's what I'm aiming for well, tomorrow. Okay, but that's a rough overview, and today is supposed to start with kind of trying to get a feeling for what the right-hand side is. And in order to do this, I would just want to, oh, that's not my first paragraph. I want to restrict myself, at least in the first place, to the GLN case, and then maybe make some remarks tomorrow how to generalize from the GLN case to an arbitrary reductive group. Okay, so let G be GLN, and C be the completed algebraic closure of QP. And attached to this, we know how to form the Fargues-Fontaine curve. So that's a, well, in some sense maybe two-step procedure. You form a curve that you usually call Y, which is spar of the width vectors of OC flat, and you remove the divisor given by P and the Teichmüller lift of some pseudo-uniformizer. And then you can just mod out the action of the Frobenius. And you see that by functoriality, the whole thing is still acted upon by the absolute Galois group of QP. Okay, even in a continuous way, even though I will not make this continuity too precise. And I want to stress as well that there exists a distinguished point called infinity in the Fargues-Fontaine curve, which is stable under the Galois action. Well, the residue field at this point is just C. And the complete local ring at this point is known as Fontaine's ring beta 1 plus. So it's kind of, basically infinity is defined by the usual theta map of Fontaine. Okay, so that's a geometric object. And well, while the board is still down here, I want to note that, of course, but that I guess was clear to everyone, these rings come equipped with a Galois action that in this picture is just there because the point at which you complete respectively takes a fiber is stable under the Galois action. Okay. So here's my definition of this kind of p-adic version of the stack of L parameters in the GLN case. The stack LS, well, it's maybe a definition / proposition, N, and then Fargues-Fontaine, and I maybe should rather write it as something attached to the group GLN, is the category fibered in groupoids. On Wilk QP, which are rigid analytic spaces over QP. Okay, and what kind of stack is this? LS, GLN, oh sorry, and Fargues-Fontaine takes a rigid space S, and I want to map this to Gal QP equivariant vector bundles of rank n over S times the Fargues-Fontaine curve, where I just let the Galois group act, of course, on the second factor. And of course, because all actions are actions of topological groups and all objects are of kind of, or all kind of structure sheaves are kind of topological objects, this Galois equivariant structure, of course, should have a continuity property that I will just kind of not state explicitly and completely swipe under the rock for the purpose of this talk. Okay, but that's the definition, and maybe the way I put it, a first proposition is due to justify my name, namely it's indeed a stack. Okay, so LS and FF is a stack for the tau topology. On rigid spaces. Well, it's basically a stack for any topology for which vector bundles satisfy descent. Okay, so you could even take something bigger. What? I don't want to go into discussions about the generality of the topology that you might want to put. Etal is perfectly fine. Okay, so let me give you an example what this looks like in the GL1 case. So if n is equal to 1, let me write T for the, well, let's say first functor of locally analytic characters, of continuous characters of QP star. Okay, so that's a function on rigid spaces. So that's a space of continuous, in fact, equivalently locally analytic, it turns out, characters of QP star. And because QP star is the same thing as ZP star times P to the Z, it's not so hard to see that you can write it as the product of the space of continuous characters of ZP star with a copy of GM, where GM is kind of the widget space GM over QP. Okay, and then ZP star has a nice property of being a compact group. So you can explicitly write what this looks like. Namely, on the level of formal schemes, you can take the completed group ring of this formal group. Of this compact group. Take its formal spectrum, so that's the thema-local complete Noetherian ring. You can take its formal spectrum and then the widget generic fiber. Okay, and it turns out, just because this thing is so nice and so easy, that this is just a finite disjoint union of open unit disks. Okay, so you have a space or the space of continuous characters of QP star. And what has this to do with my object over here? So by local class field theory, we can construct a map from my T up there to the stack I want to study in the rank 1 case that I want to denote as a character delta mapping to O of delta. Okay, that induces, so that I will maybe describe over there because I need a bit more space. So for delta in T of spar A for, say, some kind of affinoid widget space, i.e. delta as a character from QP star to A star, we write delta as a product of delta 1 and delta 2, with delta 1 being anonymified. Saying that delta 1 restricted to ZP star is trivial, and delta 2 of P is 1, or would be enough for the construction to say that it has norm 1, but like we can obviously kind of find a construction such that this is just 1. And just because delta 2 of P has norm 1, you can see that delta 2 extends to a continuous character. Let me maybe write delta 2 tilde, not just from QP star to the absolute Galois group along the reciprocity map. Okay, and then we can define what this sheaf of this equivariant line bundle is in 2 steps. That's maybe the most explicit way of saying what you get. Then O of delta is defined to be O of delta 1 tensor O of delta 2, of course, with O of delta 2 is just well, you take the structure sheaf and you twist the Galois action by this character that you have at your disposal, which is a character of the Galois group. Okay, so how did I write this? I just wrote what I said orally. Let's see whether I'll succeed to put a formula. So let's just write it like this and say the Galois group on the left factor has its natural action, and on the right-hand side via delta 2 tilde. So if you have this extension, it's kind of obvious what you do or what you want to do. And I'll put this down again in a second. If you don't have this extension, you have to do the detour along this curve y up there. So O of delta 1 is the descent of the phi, gal qp equivariant line bundle on y Fargues-Fontaine times spy. Okay, and what is this line bundle? You just take O y Fargues-Fontaine tensor hat A again, and the Galois action. So the Galois action is purely on the left, and now you have to say what the phi action is. So the Galois action is here only on the left factor. And the phi action on the left factor is, of course, the natural phi action. And here phi acts via delta 1 of p, or via multiplication with delta 1 of p. I can't swap these, can I? Oh, I can. Okay, so this kind of, well, in some sense, an ugly two-step procedure where you first have to split your character into two parts and deal with both parts separately, but that's maybe the most explicit way how to describe what the equivariant line bundle looks like that you want to attach to a character like this. Okay, and then it's the theorem of Kedlaya, Potters, and Zhao. That this map induces an isomorphism. Well, they don't phrase it in terms of these stacks, but that's essentially what the theorem says. This map induces an isomorphism of T divided by GM for the trivial action. That's the stack quotient for the trivial action. With this stack that I introduced and that I want to study. Okay, so at least for the GI1 case, that's not a scary object. You have a pretty explicit chart by a given rigid space with a trivial action of an easy rigid algebraic group. And even the space is completely explicit. There's a finite disjoint union of products of GM with an open unit disk. Okay, so like GI1 is not supposed to be scary. And on the other hand, it shouldn't surprise you that for the description in the GI1 case, you want to use local class field theory. Yes? Oh, thanks. It's a nasty feature that they kind of don't go up arbitrarily high. Unlike these. Okay, and I think I want to return even to kind of a sketch of a proof of this theorem a little bit later. As well, an application of some concepts that I want to introduce now. Okay, so namely, I want to talk about two variants. Of these bundles on the Fargues-Fontaine curve. Namely, there are two of these. If you have your vector bundle, your equivariant vector bundle, and you have a point which is stable under the group action, you can complete at this point, or you can take the fiber at this point. Okay? And I'm just writing down, in some sense, the stacks which are supposed to be the target of the induced maps. Okay, so let me write down the following two variants. LS and beta 1 plus. That's also supposed, like, these are all supposed to be stacks on rigid spaces. I just give you their values on affinoids. Spar A is mapped to spar A is mapped to finite projective beta 1 plus tensor head A modules together with, well, I said I will completely ignore this, but let me maybe just put the word on the board where it's due, plus a continuous and semi-linear Gal QP action. Okay, and this is the stack is designed so that I get the following map. I have my stack of vector bundles on the Fargues-Fontaine curve, and there maybe I have some equivariant bundle E. And what I want to do is I want to complete at the point infinity, and where I naturally land is, well, by definition or construction, this guy over here, okay? And that I want to have this map is the reason for this definition. And what you can do as well, instead of completing, you can, of course, also take the fiber. Okay, so there needs to be a target for that map. And that's literally the same with beta 1 plus, of course, replaced by C. Oh, something I always forget, or very often when talking about things like this, is that the projective modules, of course, are supposed to have rank n. And then you put the very same thing. Okay, and that's designed so that you get a map to this one. And then you get a map further down to the affine space, which is given by the characteristic polynomial of the cell operator. or theta then, whatever. Okay, and I maybe briefly recall, well, this is really just the classical sen operator, and then you have to work a bit or think a bit or read in the literature in a paper of Berger and Colmes that these constructions work in families with affine algebras as well. Right, so that's kind of what you get. Okay. And right, I guess I want to give the example of what these maps look like in the GL1 case. Okay, so in the GL1 case, well, we have this nice explicit chart. So let's see what's happening on there, on this chart. T to LS 1 Fargues-Fontaine to LS 1 beta 1 plus. And I will tell you a little bit what these guys here are. Well, it will turn out that for GL1 they're just isomorphic, but just for GL1. And I'll discuss this a little bit later. This lives over A1. And so if you have some, maybe a tiny bit of more space. Why didn't I move this to the right? You have T, and you have delta here, a continuous character. And in this case, this continuous character is automatically locally analytic. Okay, whatever that exactly means, but it means that you can take its derivative at 1. Okay, and that's what this map, what this composition actually does. Okay, so that's what this map does. And in terms of these charts, you can make this completely explicit. So it is on the board. So T has this product decomposition, so I can just project to this disjoint union of open unit disks. Okay, and then it turns out that on each copy of the open unit disk, this map to A1 is just given by the logarithm. Okay, so that's kind of the complete explicit description in terms of this chart of what these canonical maps and stacks look like in the GL1 case. All right. Okay, So, sorry? What these things are? So I didn't really understand the question, but I will say something about this. And in case I don't clarify your question, ask me again after having said something over here. So there's a description of or some kind of partial description of as LS and C and LS and beta 1 plus, which is a theorem of joint work with Ben Hoyer, of which I guess at least today I will only give the rough formulation. So LS 1, no, not 1. NC is état locally on A to the n isomorphic to the stack GLN mod GLN. Well, of course, I would have to say how this sits above the affine space. So this is a stack of vector bundles together with an endomorphism. Okay, and what I can do is, well, take the characteristic polynomial of this endomorphism, which is mapping to the GLT quotient, GLN mod GLN, and which is maybe in the case of via the characteristic polynomial naturally identified with the affine space. Okay, so état locally, these two things are isomorphic, and the essence of the theorem is that état locally this the essence is état locally as well, say an object M in LS and C of spar A can be reconstructed from its Sen operator. Okay, so that's maybe the informal statement of this, well, kind of formally and mathematically correct statement. And there was a variant for beta 1 plus, LSN beta 1 plus. Is état locally isomorphic on A to the n isomorphic to a stack that I want to call FLDN, formal logarithmic derivations. We'll define on the next board. Well, and I should tell you how this maps to the affine space. But this map just factors through that stack up here. If the question was what that guy is, that's going to be defined right here. I just wanted to finish the statement in a complete parallel fashion to the one above.
And this AN is the same AN as on that board, right?
Sorry?
This AN is the same AN as...
Yes, yes. There's just one AN. And well, I mean, like, you are right that you should complain about the use of an. I should have always written kind of this GRT quotient, Lie algebra by. But I guess in the GLN case it's convenient. Hmm? The big eraser. Oh, you're saying I'm too slow in erasing. You are impatient. Okay. So where FLDN is a stack of formal logarithmic derivations, okay, so it's a stack of formal logarithmic derivations, and okay. I mean, it's a more algebraic object, hence I could define it on spec A for any ring A, but as I'm in this rigid analytic world, let me not introduce some confusion by writing spec. So these are finite projective A power series T modules, lambda of rank n, together with a map partial lambda from lambda to lambda, which is a derivation above T ddt. Okay, so something which is maybe way more explicit because it's defined in things that rather just look like linear algebra than these kind of complicated objects with involving beta 1 plus. So that's kind of my some kind of état local model, explicit in terms of linear algebra of this stack of beta 1 plus bundles. Okay. And there is part 3 to this theorem that unfortunately there is this, well, what means unfortunately? I mean, like, there is this état twist in the business. Okay, and you can't discuss it away, and it's there, and it's a really non-trivial état twist. But at least if you are in the neighborhood of integral Hodge-Tate rates, so if the zeros of your characteristic polynomial of the Zen operator are integers, then this état twist goes away. Okay, and that's something I want to state. So let X in the affine space. Recall that the affine space for me is a space of characteristic polynomials. So this corresponds to a polynomial with roots lambda 1 up to lambda n. And I want to assume that these roots are integers. Okay, so then, in fact, this état local thing goes away in some sufficiently small neighborhood of the point x, and then LS and C is just isomorphic to GLN mod GLN in a neighborhood of x, and the same in the de Rham case. And in fact, you can, well, it's maybe not unexpected that you can take these neighborhoods to be the same thing in both of these cases. Okay. And
But you mean then there's a rigid open neighborhood, or
yes, in a. Thanks. And open. So analytically open. Right. So you don't have to do any étale neighborhoods in order to trivialize this étale twists that you have or that you see. Woo! You mean that the punishment will come when not from above, when I try to pull it down? Yes, right. Let me postpone this question as well. So the question was whether I can explain the reason for this. I will give you the description what at least the formal completion of the stacks look like at some point. And then, in some sense, one answer to your question would be, because this description, what the completion looks like, works the same for both sides. But let's see whether I will be able to answer this question in maybe a few moments. Okay, so I want to make a few remarks about the GL1 case. Okay, so if you look at these kind of linear algebra objects, vector bundles with an endomorphism, respectively, this logarithmic derivations, it's an easy computation to see that FLD1 is just GL1 mod GL1, so this projection map is an isomorphism. I didn't write upstairs what this map is, but this map, I guess, clearly should be just given by modding out T. Okay, so I wrote it maybe here. Lambda goes to lambda mod T times lambda with the endomorphism induced from your derivation. Okay, so you have a map, and for GL1, it's kind of very easy to check with bare hands that this is an isomorphism. It's just linear algebra. And so it follows formally. So by applying the theorem above, well, you could have proven it by p-adic theory as well, of course. But well, I've just put in all this kind of p-adic theory into the proof of the theorem, and can then certainly say that what I've wrote over there is just a formal consequence of this linear algebra computation. Okay, and what I want to use this thing for is we can use this construction that's something I like quite a lot, even though it's kind of not a new theorem or kind of spectacular. We can use this construction to give a new proof of this isomorphism, which is a theorem of Kedlaya-Portas-Zhao up there. And I want to give you a sketch in order to, in some sense, see or let you see how these things work in action. Okay, so the hard part in the theorem is to show that any Gauss QP equivalent line bundle L in LS1 FF of, say, some S, etat locally on S lifts to T. Okay, so that's the hard part, to show that this has a chance to be an isomorphism because it's a surjection locally in the étale topology. And how can you see this? Using exactly this diagram over here. Well, you do this by boiling it down to some other hard theorem maybe, but where are my notes? Yeah, okay. So we have LS1 Fargues-Fontaine, and we map this down to A1, and here we have the space of characters. And here we have a map that I maybe want to call omega, and which is just a map from the board over here. And we call, by the explicit description that I gave over here, that this is a smooth map. Okay, this is smooth. Okay, and you have your equivariant line bundle here. It maps to some point x in A1 down here. Okay, but as this is a smooth map, this means that etat locally on S, you can lift this S-valued point here to an S-valued point here. Okay, so etat locally can lift x to some delta in T of S. Okay, and we replace L by L tensor O of delta inverse. So I twist by this. And what I've achieved by this is that I can assume that x is 0. Okay, so we may let x is 0. Okay, but what does this mean? Okay, so this implies, if you look at what I told you about these stacks here in the middle. So this one in the neighborhood of this integral point, x being 0 is certainly integral, just looks as, well, GI1 mod GI1. And this one is an isomorphism as well. This GI1 action here is trivial. So this exactly tells you that L completed at infinity is a trivial beta1 plus bundle. Okay? Okay, so i.e. L is what you would like to call the Rahmen of Hodge-Tate weight 0. Okay, I didn't formally introduce it, but that's literally what this means. And now, okay, you don't get away without applying something strong. We can apply the p-adic monodromy theorem, which says that the RAM is the same thing as potentially semi-stable. Okay, so this is certainly using something, and maybe even, again, work of Berger and Colmes, that this p-adic monodromy theorem works in kind of families over avienoids, that L is potentially semi-stable. Well, of Hodge state rate 0. Okay, but what does potentially semi-stable say? Sorry, this is maybe now just an argument for those who are quite familiar with what these words mean. Potentially semi-stable means that it comes by an explicit construction from some more linear algebra datum, from kind of phi n Galois modules. Okay, so this is in particular L is the equivariant line bundle attached to phi and gal QP module. Okay. Okay, and I will maybe finish over here. Okay, but it's easy to check. That, well, what is now your source in order to construct this line bundle L? Well, as I forced x to be 0, they certainly have to live on the fiber of these. Okay, so I take my characters, which are on the pre-image of 0. So these are, well, because the derivative is trivial, these are the smooth characters. Of QP star. And it's a rather easy check that these are surject onto, well, these of rank 1. On these rank 1 phi n gal QP modules. Okay, and this gives you a proof of the theorem of Kedlaya-Potras-Zhao that I wrote down earlier. And the nice feature of this proof, I think, is that if you think about it, it directly, completely uniformly works for all tori, not just for GM. Okay, in case you define your objects for arbitrary groups. The last step uses class field theory, yes. But, well, I mean, it has to use class field theory somehow, as already class field theory was kind of built into the very definition of this map. And it uses class field theory in exactly the same manner how it goes into that. Well, I mean, like, that's maybe supposed to be a statement about families or stacks. Well, because I didn't put any filtration. Well, I mean, like usually kind of for potentially semi-stable things, you would put kind of filtered phi and Galois modules, but I have just Hodge-Tate rate 0, so the filtration goes away. And because I'm rank 1, certainly the n would go away as well, but it's kind of, I guess that's the usual way to write it. So. Sorry?
If you had the filtration in the picture, you still have this such a
If I would put a filtration over here, then here you would have to put kind of locally algebraic characters or something like this, right? Which then would be kind of the pre-images of the integers embedded into A1. Well, I mean, like, so the question was whether the step was necessary. The step was certainly necessary because x could have been anything in A1, not integral or anything, right? I mean, like, it's definitely necessary to use the smoothness and look in this twisting thing, which comes from the fact just this map is smooth, so that you can have kind of any chance to pass to this world that you can describe in terms of phi n modules or something like this. Okay, moment of truth. No problem. Okay, so, I mean, I don't want to claim that this is the most elegant and elementary proof of the theory of Kedaya-Potter's Jiao. In particular, it uses kind of this kind of heavy theorem that de Ramis implies potentially semi-stable. Okay, so in some sense, so in this sense, it's way more complicated, but I wanted to give you this as some kind of application of the objects that I introduced. So that you can, in some sense, see what these geometric things mean in action in some example. Okay, so I want to talk a little bit on the geometry. Of LSN B to 1 plus. Okay, so what? Well, as they are état locally the same, it's for the local geometry equivalent to talk about these two stacks, where I guess I don't have to say much about the geometry of that one. So it's rather about the geometry of the stack of formal logarithmic derivations. So we have maps from GLN to FLDN. And what does this map look like? I can take some x, which is an n by n matrix, for some ring A. And what do I want to map this to? Well, I want to map this to delta x on at to the n to at to the n, such that delta x restricted to a to the n is just x. So in some sense, just takes the unique extension of this endomorphism of a to the n to a logarithmic derivation. So it's kind of, I guess, easy to write down that you can do this. And the second map that I have, okay, I already put it quickly up there. I have the map that takes lambda and partial lambda to lambda mod t times lambda and partial lambda mod t. okay, which is now linear endomorphism of this vector bundle lambda mod t times lambda. Okay, and I want to analyze a little bit what the stack looks like, respectively what this map looks like. And this map is often very close to being an isomorphism. So let's again take x in a to the n corresponding to a characteristic polynomial with zeros lambda 1 up to lambda n, which now I do not ask to be integers, at least in the first place. Okay, so and let's assume it's not the it's the case that they are not integers. Then it's not hard to check that if I complete the space at x, the map to the completion of this kind of very easy and basic stack GLN mod GLN at x turns out to be an isomorphism. Okay, and that's just linear algebra. And if you look at the above theorem, then this formally implies that the same is true for these versions with beta 1 plus and c. Okay, so if I put here this stack of beta 1 plus representation and I complete over x, and I put here the stack of c representations and I complete over x, and this map becomes an isomorphism if I ask for this condition.
Sorry, again, what's that condition? Minus the I dash and the j not a c. Minus, okay.
Ah, sorry, okay.
I don't know why.
It's yeah. You mean this completion?
Yes.
So this formal completion for me, this should mean you restrict the functors to these are in some sense FLD, and like both sides are functors with values in groupoids over a to the n. Okay, so your test objects come with a map to a to the n. Okay, and this formal completion is just supposed to mean that you restrict this functor to those maps to a to the n that topologically or set theoretically factor through this point. That's what formal completion means. Okay, and so let's do the opposite extreme. Let's do the extreme where lambda I minus dash, lambda I dash lambda j is an integer for all ij. Sorry. But let's say that they are pairwise distinct for simplicity. Okay, so then I want to describe you as well what this formal completion looks like. Okay, sorry, n completed at x. And this now becomes isomorphic to GLN tilde mod GLN completed above 0, where I'll put it over there. GLN tilde is a Grothendieck resolution. So which parameterizes an endomorphism together with a stable flag, so that in particular, if I form the stack quotient, this naturally becomes the the corresponding quotient for a Borel subgroup. Okay, and choice of a well gives you an identification like this. So that's what it looks like. And I want to tell you why this looks like this, and this way maybe as well answer Vita's questions about how to think about this, well, isomorphism of this kind of completion with the one for beta 1 plus representations in the case of integral Hodge-Tate weights. So I want to put here v comma x and GLN mod GLN completed at 0. So I take a vector bundle together with a nilpotent endomorphism. Okay, and then I want to take, in addition, well, I know what partial x now is supposed to be. Okay, so this is a derivation on, I can form V tensor A. I can kind of constantly extend this vector bundle from the special fiber to this formal disk. And then by the above construction, I know what kind of the corresponding logarithm derivation extending my nilpotent endomorphism is. Okay? And I now just want to take a modification of this. So I take a del x stable lattice and, well, the same thing I would before, but inverting t, so Laurent series t. And now my x or my lambdas have to go somewhere. Okay, and I want to say that these are of relative position lambda 1 up to lambda n with respect to the standard lattice. Okay, so I consider my kind of constantly extended logarithm derivations, and I want to modify this by some lattice, and this lattice is supposed to be in some fixed affine Schubert cell in the affine Gauss-Mannion. Okay, and I will then get a map over here by just kind of mapping it to this lattice lambda to this lattice lambda, and I get a projection down here because kind of these Schubert cells were mapped to flag varieties. Okay, and it turns out that this map here is an isomorphism, and it turns out that this map here is an isomorphism. And that's where this description comes from. And if you think about this description, that's, well, so if you write down the exact same statement for BD1 plus representations, then you find that this is in some sense exactly how you want to attach BD1 plus representations to filtered vector spaces. Okay, BD1 plus representations of integral Hodge-Tate weights to a vector space with a filtration. The usual functor of Fontaine that kind of maps something to Dideram of. So maps the BD1 plus representation to its Dideram thing. Okay, so that's kind of in some sense basically the counterpart of this isomorphism. Okay, so I have.
Any modification will automatically be Nabla stable, or is it something you?
Sorry?
Like, so you modify the relative dimension
No, I ask this modification to be stable under.
Yeah, but is it hard to ensure this? Is it hard to ensure this?
Well, okay, so no. And that's in some sense the essence of this statement that this map is an isomorphism. So if you would kind of just put all lattices, you would end up in kind of GLN for this part, and then kind of taking the projection from this Schubert cell would just map you to a flag variety. Okay, and then the fact that this lattice is supposed to be stable will just translate to this flag to be stable under the original endomorphism X. Okay, and this is kind of, okay, like, I don't know whether you now would say it's kind of hard to ensure this or not, but it's kind of, it's a very explicit condition. And it's kind of just, yeah.
When you have part 3 of this theorem, I guess part 3 is not there anymore.
Sorry, say it again.
You had part 3 of your theorem with Euler.
Yes.
It's not written on the board anymore.
Yes.
There was no condition that the lambdas are distinct. But here, there was a condition that the lambdas are distinct.
Yes, this is kind of the third bullet point, where I tell you what you should think of this construction in general a little bit. So in general, for general x, respectively lambda 1 to lambda n, well, I will not give you the most precise version of this, but this thing here decomposes as a finite product of things that you've seen before, but here you don't put kind of a full Grothendieck resolution, but a partial Grothendieck resolution. Okay, so that's kind of how you can completely explicitly describe at least the formal completions. Okay, and here the consequence. Is that the stack FLDN is formally smooth. Okay, so all its formal completions look like the formal completions of smooth Artin stacks. But caution, FLDN is not an Artin stack. Okay, and given what I said, it's in fact even very easy to see and to verify that it can't be an Artin stack, because you have the map GLN to FLDN, okay, which I erased, but which is kind of this kind of taken. It's still there? Ah, yeah, right. Exactly this map up there. Okay, and because I now have kind of perfect control of what happens on complete local wings, this tells me that this is, well, up to dividing out by some GLN. This is an isomorphism on formal completions most of the time, if my lambda I minus lambda j are not integers. But if they are integers, it becomes some kind of a weird map. Okay, so this is a versal map if lambda I minus lambda j is not an integer, and it's not a versal map, so formally smooth, if lambda I minus lambda j can be integers. Okay, so this map violates one of Artin's axioms, so this is kind of not, so this violates openness of versality. Which is among Artin's axioms for Artin stacks. So any Artin stack which would roughly satisfy that the locus where this map here is formally smooth would be open would be an open subset here. And you can see from the explicit description that I gave that this can't be the case over here. Okay, so but at least you can see FLDN is a pro-Artin stack. Okay, this you just see by, in some sense, truncating by powers of t. Okay. And how much time do I have? 5 minutes. So that's kind of annoying to have 5 minutes left when I've just finished something. Okay, so let me just very quickly try to say something about a corresponding Hecke action. Okay, and this is over here. This is about a Hecke action. Let me maybe put this a bit in quotation marks because it takes place on the Galois side. And you should be surprised to see a Hecke action on the Galois side. But it kind of formally looks like what a Hecke action is supposed to look like. So I consider the Hecke stack for beta 1 plus representations. Okay. Just Hecke n beta 1 plus, which maps some s to tuples lambda 1, lambda 2, and then maybe some xi with lambda I are just beta 1 plus representations, and xi is an isomorphism after inverting t. Okay, so then I get the following diagrams. Three diagrams. Hecke n beta 1 plus times the fiber product over these local systems. And then you have three projections to the Hecke stack. P12, P1, 3, and P1, 2, 3, 2. Okay, and this looks like I now have a triple, lambda 1, lambda 2, lambda 3. And I want to map this to kind of the corresponding pairs. Lambda 1, lambda 2, lambda 1, lambda 3, and lambda 2, lambda 3. Okay, so that's the one obvious diagram I can draw. Then there is a second diagram that I can draw, namely okay, and this is kind of lambda 1, lambda 2 with respect. So let's call this Q1 and Q2. And I project to the corresponding factors. And there's a third diagram. Which kind of lifts this to sheaves on the Fargues-Fontaine curve. So I have LS and Fargues-Fontaine. And I take its product, the fiber product, over the stack of beta 1 plus representations with the Hecke stack. And then I have the projection to LS and Fargues-Fontaine, which is kind of given by the modification of a vector bundle. This is a projection, and that's the modification of a vector bundle. By a given lattice, so the usual Wolfe-Laszlo construction. And then I want to just write up a formal consequence of the constructions. The category of coherent sheaves on this Hecke stack is a monoidal category under convolution. And let me quickly write F convoluted with G by definition is PR13 lower star of the tensor product of the other two things. And this monoidal category naturally acts on the coherent sheaves of LS and beta 1 plus, and on the derived category of coherent sheaves on the Fargues-Fontaine curve. Like by taking something here, pulling back, take the tensor product and pushing forward, respectively doing the same thing over here. Pull back a sheaf, kind of tensor with a pullback from a sheaf on the Hecke stack and pushing forward along this modification map. Okay, and what I want to do next time is, as I have a pretty explicit understanding of what these stacks look like, I can very easily and nicely describe them. I want to kind of, in some sense, take advantage of this action and, and describe this action for you and kind of tell you what this is supposed to give in view of local integral representations, and then maybe draw some application or conjectural applications to p-adic automorphic forms. Okay, thank you.
Okay, thank you. Any question?
In the last board, it was Hecke action. So which parts? This looks completely formal.
Yes.
Where is there some input? And where is the input?
So whether there's some input in going into the statement that there's a monodal category and so on. This is kind of formal. I mean, there was an input in the sense that I wrote here bounded and coherent, and I have to argue that this is preserved, and that boundedness. Oh, it's not me. Okay. That boundedness is preserved. That's precisely due to the stack that I wrote up there. That these stacks are formally smooth. Okay, so that's the input that you need in order to see that this, well, okay, sorry. Well, of course, all functors are derived, right, in here. It's a statement about the derived category. So that this derived fiber product preserves bounded complexes. So it's just due to the fact that you can see that one of these stacks is formally smooth. And then there was something due where I was cheating a little bit. I mean, at least those who are kind of familiar with the formalism that in any case of a diagram like this, you get some kind of Hecke action. You would maybe actually, in your sheaf theory, expect some lower Schwick here instead of a lower star. Okay? And I want to argue that this goes away because this map here is proper. That's not quite the case. But that this is not quite the case has to be built into the correct definition of what this is actually supposed to be. Okay, so these are coherent sheaves on some stacks of modification. And I want to, in fact, or should, put some additional finiteness condition, namely that all my sheaves are supported on some finite stratum where the relative position of the two modifications or two lattices is bounded by something. Okay? And once you put this condition, you see it doesn't matter whether you put a lower Schwick or a lower star, and in particular this also preserves coherence. Okay? Because the map becomes proper on the support of these sheaves. So there is something which goes in here, which I kind of am hiding a little bit in the short and informal statement of this result.
Any other question?
This description of this equivalent plus stack and the partial Moduli, do you get it also for
Whether there was a description like that upstairs for any reductive group, so of this stack of formal derivations or this stack of B1 plus representations, yes. You get, I didn't even define what these objects are for an arbitrary reductive group, but if you properly set up the definition, there is some description like this for any group, yes.
So maybe I suggest that if you have any other question, you ask directly the speaker. Thank you. And we resume at 10:50.